welcome to this tutorial. Today we want to look at a very interesting thing. We want to look at how we solve homogeneous ordinary differential equations. Before we start our class today, kindly subscribe to this channel so that every time we post a new video or tutorial, you'll be the first one to get the notification. In case you have any question on the previous tutorials, kindly leave a comment down there. If you have a question that or a challenge that you need assistance from, you can leave it there. I can do it for you and guide you on how to do it. Now, welcome to today's lesson. The solving homogeneous ordinary differential equations. Homogeneous ordinary equations. So we have to get some note here. A function of this form of x and y is homogeneous to a given degree k if this is true. So if you can express that function from this side to this side and it can be explained that way, you'll say it is of degree k. So you can see that degree k is up here, up there. So you can see t to power k, and that k is the degree for that. So for example, then we can demonstrate this while with an example. So if you have given a function fxy of this kind, what you need is to express this in this form, and by doing that, where we have x, you substitute with a t, ty, so on and so on. Then expand normally, and after expanding, you factor out the common one, and the common factor here is t to power 3. And if you look at what is left on the other side here, you'll find that is actually the function of x and y that we end. So you can see our function of xy have been expressed to the required form, and if that can happen, then that is a proof or a show that this particular ODE is homogeneous. And because now it's homogeneous to which degree? It's homogeneous to of degree 3. Is homogeneous to t to power k. So our k in this case here is 3. So it is actually a homogeneous equation of degree 3. That's noted. We proceed. So let's get a definition of a homogeneous equation of first order. Homogeneous equation of the first order. So a first order differential equations, of course, we know this is the form of the first order DEs. We say it's homogeneous if you can expect that form. What does this mean? It is a first order homogeneous equation if it's of degree 1. It's of degree 0. It's of degree 0. Why am I saying 1? Is because the k is 0 in this case, so our t is to power 0. So that gives you 1. 1. So it's like here we have a 1 there. So that is actually t to power 0, k being 0. So if you get it for degree 0, then you know that is a homogeneous equation of degree 0. And that's the first order homogeneous differential equation. So you'll find that how do we get solution of homogeneous differential equations? We know it's actually that, and if suppose that is an homogeneous equation, then you can see that it can be written in this form, not that form. It can be written into form of dy over dx being equal to g to bracket y over x. So that's very not. So if it's a first order homogeneous equation, then it can be in that form. So what you need to do there is to let whatever in the bracket in function of g with this y over x to be equivalent to v, be equal to v, and rearranging, get y is equal to that. And if you get and dy dx of this, remember this is a product rule, of course, so that's the reason we are having this kind of summation. Product rule, differentiation by product rule, derivative by product rule method. So you get that kind of expansion. So our dy dx is equivalent to that. So if you can substitute this equation in the then dy dx to this, if you can substitute what you have in this, remember this is v, dy dx is v plus x dv dx. So if you substitute that, you are basically going to get this kind of equation, v plus x dv dx equal to gv. So if you can rearrange this, and you'll find that you have x dv dx being equal to gv minus v, and again we are just trying to rearrange, and if you rearrange you find that. And if you look at this, basically this is now what we call separable ordinary differential equation. Remember in the previous tutorial we had looked on how to solve separable ODEs. So if you did not see that, kindly look up there and you can see that audio, and you follow up and be able to see how we do this. And having seen that, we can now solve this using the concept of separable ODEs. So we solve it using the idea of separable ODEs, and then at the end, v, we know v is this y over x. We substitute that to that, so that we get the general solution to that. Let's look at an example. So suppose we are trying to solve this x cubed plus y cubed because on dx 3x y squared dy equal to 0. So we want to look at this. So what we need to do here is we need to check whether the equation is homogeneous. So how do you check that the equation is homogeneous? We check whether the equation is homogeneous by checking the degree of each term. So luckily, in this equation here, each term has a degree of 3. So you see x is cubed, y is cubed, and the other term is xy. So this is x is power 1 and y is power 2. So if you want the 2, you get 3. So every term, that term and this term, they are of order of degree 3. And by that fact, we say this equation qualified to be homogeneous equation. So that's simply how you can test and get to know whether the equation or the DE is homogeneous. We're just looking at the degree of each term. So next, what do we need to do? We need to rearrange this one in a way that we can now deal with it. So we put x's together, dx and dy on the same dy and dx. Arrange that. But before that, we remember one thing. We remember that v is equal to x, y. V is y over x. We know that. So in this case here, rearranging this, you can see we are able to get this. We are able to get this. We are able to get this. So try to rearrange that and see whether you can get that. And if you can get that, kindly leave a comment and ask me how. I'll show you how I'm arriving to that. I'm arriving to that. So hope everyone have seen that. Okay, so now substituting y over x with v, and y equal to that, the other relations dy and dx, that one. So in dy and dx, we substitute that. When you substitute this, you'll find we are having this. Yeah, I'm going to get that. And now we try to rearrange this, because now we have simplified this one to a more simple way, to one separable equation. So when you rearrange that, you'll find that it can be separated, and therefore you see this is now a separable dE. So a separable dE. So after integrating both sides, of course, you'll be able to get this and also get this. So what do we have here? If you multiply by negative, so here everything multiplied by -2. That's the reason you can see this. Here, just to mention here, integrate this by parts. Again, if you have some question on this part, or now this one is becoming this, kindly leave a comment. I'll be able to show you how we arrive to that. But if you integrate that one, you are basically going to get that as the solution. And that gives us this, because of logarithms and logarithms here, they cancel. So we have that, which is basically our solution to our dE. Is the solution to our dE. Is basically a solution to our dE. And that's how we have solved the homogeneous equation dE, using all those steps. So in case you have a question on this, just leave a comment down there, and I will be able to respond as soon as possible. And if you have any other question, not really this one, you can even leave it there, and I'll be able to look at it and help you in getting that kind of knowledge. So thank you for today. Until next time, kindly subscribe. Don't leave the page without subscribing. Thank you for your time.